All right. So for those of you who sat through my little spiel on the differences between inner products, norms, and Hilbert spaces, or metrics, I should say, and then their associated spaces, this might be like boring, or this might be obvious because I talked about it, but I'll start from scratch. So we're talking about a special kind of vector space, right? Or like if you want to think of it like a subset of the vector spaces, in a way. So if we have a vector space and we have this is a shitty marker, we have an inner product is what we call it. These two together, we call it an inner product space. And maybe you're like, what exactly does this mean? Well, like maybe you're wondering, like, what do we mean when I say like V with a product? Like that's kind of a weird notation maybe for some of you. It shouldn't be, because we've already talked about something very similar, right? We said a vector space is a set V. So here V is a set, right? That needs to be paired with two operations, plus and scalar multiplication, right? And then it has to meet a set of rules, right? Inner product space is similar. It's just, you get a third operation in a sense, right? That third operation, we call it the inner product, and it's similar, well, it's an example of an inner product is the dot product from like Euclidean vectors. So we define the dot or the inner product. It takes two, sorry, I should write this a bit better. If V is a vector space, it takes two vectors, so V cross V, right? And it outputs, anyone know what it outputs? Yes, from where? Yes, from the field. So it's a function, it takes in V cross V, so two vectors, and it outputs a field, or something from the field. What do I mean by V cross V? This is from discrete, I think. These are two sets, and I'm taking the cross between them. Yeah?
That's set of all ordered pairs?
Yes. So in other words, it's just two vectors, right? U with V, and that's sort of what's going into our inner product. Just a weird notation. You might also see like V squared. I really don't like that notation because then you think it's like vectors or something, right? But yeah, V cross V. Cool. So what makes this thing an inner product? Of course, there's definitions and there's rules, right? Just like everything else in this course. So for something to be an inner product, the first thing, we call it conjugate symmetry. So it requires that if you take the inner product of U and V, then that equals the inner product of V with U conjugate. What do I mean by conjugate? Does anyone know?
So, in a complex polynomial, imaginary number.
Sure. The imaginary part, right? So if I have a complex number A plus IB, then the conjugate of that is A minus IB. So you just flip the sign in front of the imaginary part. What happens if our field is the real numbers? What does this conjugate symmetry become? Sorry? If it's real numbers, yeah, if it's R. Yeah, you can just swap them however you want, right? Because like there's, if you want to think of it, it's like A plus I times 0, which is just A plus 0. And if you take the conjugate of that, that's just a minus I times 0, which is just a minus 0. It's the same thing, right? Cool. Okay. What else do I want to talk about? Part B. So additivity in the first slot. So everything that we're talking about in terms of like linearity is going to be in like the first slot of the vector space. And that's important. It's not important when we're talking about real vector spaces, but it is important when we're talking about like complex because of that conjugate piece, right? So what does additivity mean? Does anyone know? Like just in general, what I mean when I say additivity? Yeah.
Isn't it in the first one, it's U plus V with W?
Yep.
And then the second one is two separate inner products. It's U, or U and W and U.
Yep, exactly. Additivity means that you can split something up under addition. That's all it is, right? So if you have like two things that are, or if you have something that's additive and you have two things added together inside, you can split it apart, right? Maybe think about like derivatives as an example, right? If you took the derivative of f plus g, it was the same thing as like the derivative of f plus the derivative of g, right? Does that make sense? There's a second piece that goes with additivity, which is homogeneity. And again, it's in the first slot. Does anyone know what homogeneity means? It's a weird word, I know.
When you take, say if you take a document,
So it's when you take like a constant from the field and multiply it by a vector, like that, right? Sort of like a scalar multiplication, if you want to think of it. You can pull that scalar multiple out. This u with v. Does that make sense? Part C, or part D, I should say, is, and I don't know how different instructors have different words for this one. I think the mathematical proper term is positive definiteness. So that's what I'm going to use. Positive definiteness. And I don't think you actually have to know these. I'm just writing them so that if you see something like that in a proof or something, then you know it. Positive definiteness is that u, inner product of u with itself is greater than or equal to 0. Is that right? Yeah. And the inner product of u with itself is equal to 0 if and only if u is equal to 0. Does that make sense? So the positive piece is this, and the definite piece is this, because you definitely know what the vector is if it is 0. Does that make sense? Why we call it positive definite? Cool. Okay. So like I sort of mentioned over there, we can define a few things from an inner product. So like the inner product of u with itself, we define that to be the norm squared. So if you take the square root of the inner product of u with itself, that gives you the norm. Sometimes you'll hear that referred to as like the induced norm on that inner product space because like it's derived directly from the inner product, right? There's, like I was mentioning earlier before class, there's a possibility that there's norms that aren't derived from inner products that still meet all the rules of a norm. But that's not something you have to know for this course. I don't think, at least, unless Mihai's teaching differently. We define the norm of u minus v, we call that d of uv. And I'm purposely not saying the word distance because a lot of people see d and think distance. The proper terminology is that d is a metric. So if you see like metric, D is a metric. Does that make sense? Any questions about that? Sort of like the distance between two vectors, but here we're talking about like very abstract vectors. So like what's the distance between two matrices, right? Doesn't really have like a concrete definition. Well, it does, but it doesn't have like a visual definition, right? We also talk about angle. Again, very abstract. Like you can talk about the angle between two matrices. So like if I take the cosine of theta, I'm going to write this, sorry. The inner product of u with b is equal to the norm of u times the norm of v times the cosine of theta. And I think that's something that you saw in 2050. The idea with that is that, like, you know, it is true that you could find the angle between like two vectors using that, but in the abstract, you can find the angle between two of any vector, right? Like any abstract general vector. Maybe it's the angle between two matrices that you're thinking about, right? That doesn't have any like physical interpretation, or the angle between two functions that doesn't have a physical interpretation, right? But yeah. Cool. There's a couple inequalities that go with this. I'll write them over here. The first one is Cauchy-Schwarz, which, to be fully honest, I can never remember. I know that it relates, so a good thing to remember is that it relates inner products to norms using an inequality. So Cauchy-Schwarz is that the absolute value of u with b, and notice when we do absolute value, we just use one of these vertical lines, not two. Two would be a norm. So the absolute value is sort of less than or equal to the norm of u times the norm of v. And I think that should make sense, right? Because if you start at this, right, cosine of theta can range between +1 and -1, right? So if you take the absolute value of that, then it's going to range between, well, if I take the absolute value of both sides, right? We should maybe start there. If I take the absolute value of both sides, we know that by the properties of norms that these two things are both positive, or non-negative, I should say, right? So really we can write this as like the norm of that cosine term, or the magnitude of that cosine term, which means that it's going to be between 0 and 1, right? Because normally it's -1 to 1, now it's 0 to 1. Which means that if we drop that term, that like sort of implies that inequality, right? Because this side is always going to be, am I saying that right? Yeah, that side's always going to be, did I get that right? I think I did. Double check the sign on that, because I feel like I might have gotten the sign, like the inequality direction wrong. But I guess the idea is that if you drop that cosine term, then it implies the inequality. Does that sort of make some sense? That's kind of where the proof comes from. And then part 2 is the triangle inequality, which is, does anyone know it? Say it again. Yep. Yep.
Not equal, it should be.
Yes, it should be greater than or equal to plus norm of b. Yeah. Yes, that's right. This side should be greater, I think. Sorry. Like that. Yeah, exactly. And you can sort of think of this like, it kind of feels like Pythagorean theorem in a way. Yeah. So like, if you take like, say that you have like a vector A and a vector B, and these are like real vectors. This vector here would be A plus B. So it's kind of like the distance from here to here is always going to be less than the distance between the two directions, right? the size, I guess, if you want to think of it like that. It's like the most direct path, if you want to call it. Any questions about that? Nope. Okay, so from there, I'm going to do a little proof. You haven't proved the reverse triangle inequality, have you? No? Okay, good. Because that's what I was planning to do. Okay, the reverse triangle inequality. It is the norm, or the absolute value of the norm of V minus the norm of U is less than or equal to the norm of V minus U. Does that make sense? Now I'm just going to give you an outline of the proof because I don't want to write out a full proof. I think it's sort of a waste of time at this point, but actually, do you want me to write out a full proof? Yeah? Okay, then we'll do it. So let's let U and V, well, maybe first let's let big V be a vector space. I don't want to write out vector space. Actually, sorry, we're going to make it an inner product space. So we've got an inner product space. Let's let V and U be from within that big V, the inner product space. Since it's in an inner product space, we know that triangle inequality holds, right? So triangle inequality holds. Also notice that I'm like writing this in sentence form. I'm not just writing a string of equations. That's the key takeaway from this course, right? Is like, don't write strings of equations for proofs, write sentences. Cool. So since triangle inequality holds, I'm going to pick vectors sort of strategically here. So I'm going to say the norm of V plus the norm of, let's see, V minus U. So these are my two vectors, like A and B, if you want to say that, in the triangle inequality. So that's going to be bigger than or equal to the norm of the sum of the two, right? So V plus, did I get the order there right? Maybe I didn't. This should be U. So U plus V minus U. Are we good with that step? Cool. Similarly, we get, if I swap U and V everywhere, I get this. Right? I just swap places of U and V because they're arbitrary, so it doesn't really matter. I'm just writing both of them down. So then from there, we can rearrange each of these. So rearranging both yields, we get norm of V minus U, which is this term. I'm going to bring this norm of U to the other side. And I can cancel out some of these terms, right? It's like U minus U and V minus V. So what I end up getting is that norm of V minus U is greater than or equal to the norm of, let's see, norm of V minus norm of U. Do that right? Norm of V minus norm of U, yep. And the other one gives us norm of U minus V is greater than or equal to norm of U minus norm of V. Right? If I take the absolute value, well, the first thing I should note is that notice the norm of V minus U is the same thing as the norm of U minus V, right? because these are both distance. This is like the distance between v and u, and this is the distance between u and v. They're metrics, right? So really, these two sides are the same. If I take the absolute value of these two terms, they're also going to be the same, right? Because the absolute value of a difference doesn't matter what order you do the difference, right? Just get like a -1 sign out front, which the absolute value will take care of. So we get the norm of v minus u is greater than or equal to, hopefully I got that sign right, yeah. The norm of, or the absolute value of the norm of v minus u, v. That's all we needed, right? You can put a square too if you prefer. It just means end. You've probably maybe seen a square or QED or like a colored in square. There's a few different ways. A couple things I want to note. First off, I wrote that in pretty much sentences. If I was doing this for an assignment, I would write it in like full sentence form. That's what proof should look like, right? You have an assignment due next week, I think. Awesome. So that's the kind of thing I want to see, is sentences, right? If you can, as best as you can, right? I'd rather see a proof that has full sentences that has like errors in it than to see a proof that is fully correct but is just a string of equations. When you're writing a proof, this is what I tell my students in linear algebra who are just starting with proofs. Think of it like, who here has a sibling? Cool. Think of it like your sibling is, being a total idiot, and is like trying to get under your skin, right? They're like trying to poke a hole at your argument, right? And that's like their one goal, is to like, you're trying to show them this and they're trying to be dumb and come up with bad examples to try and prove you wrong, even though you're right? They're just trying to get under your skin. That's what writing proofs is like. It's like you want to make it like so foolproof that like anyone who reads it, even if they're like out to get you, they can't, because your proof is so strong, right? Proofs also have styling formats. So PF, or proof, however you want to write it, at the beginning of your proof, it doesn't really matter how you write it as long as you start with the word proof or the letters PF or something like that. And it should end with a QED or a box or something like that to show that you're done. That's kind of like starting a sentence without a capital letter. If you were like handing in like an essay for your English class, you wouldn't start sentences without capital letters, right? Same thing here. You wouldn't end sentences without periods, right? It just doesn't look good. QED is Latin for quod est demonstratum, which means I've showed it. And I like to use it because it's kind of like a mic drop. At the time, it was meant to be a mic drop. It was like, you didn't think I could do it, and I did. Boom, showed you, right? That was why they used QED. It was like a pretentious way to say I showed you. Cool. Let's go through a couple of basic inner products. I know I'm taking a lot of time. In Rn, what's the common inner product that we use? Dot product, right? So if we want to take the inner product of u with v, that's going to equal the sum over I of ui vi, right? So we just multiply each pair of entry together and add them up. In complex numbers, the inner product of u with v is, anyone know? Similar. It is ui vi, but the vi is conjugated, right? So you add the vector in the first position with the conjugate of the vector, or the entry in the first position on the second vector. So you do original times conjugate plus original times conjugate. Last one is r to the r, which are functions. Does anyone know what functions inner product, if I want to do inner product of f with g? So it's the integral from minus infinity to infinity of f of x, g of x, dx. Cool. All right. That took more time than I wanted it to, but I hope that was worth it.